Dermot Brabazon from Dublin City University.
Good afternoon, everybody. So I've got the graveyard shift. I'll try not to keep you too long here this afternoon. So I'm going to give an overview of additive manufacturing, and I only have 15 minutes now, so I'm going to concentrate mainly on polymer additive manufacturing with just a little touch on metal additive manufacturing as well. So within the Advanced Process and Technology Research Centre, we focus on production technologies, advanced materials engineering, product design, sustainability, and micro nanosystems technologies. The 3D printers that we have are mostly polymer 3D printers. There's 8 polymer 3D printers. This is the Stratasys Connect 1. It has a 20 micron resolution X, Y, Z, and it allows 3 different polymers to be printed at the same time in the same build. So it's really one of our newer systems, and it's quite capable. Roughly 255, 252, and 200 millimeters in terms of the geometry, build geometry. They go up from this, but the cost of the system is in the order of 100,000 euros, so reasonably pricey systems. We have Stratasys Dimension as well, which is fused deposition modeling in the region of 50,000 euros. Stratasys U-Print in the region of 35,000 euros. So it just depends on time in terms of the quality, the dimensional resolution that you're trying to obtain in the system, and the build area. As the dimensional resolution increases and the build area increases, then also the cost of the system increases as well. We have other 3D printing systems, and a lot of this research is focused towards I hope you can hear me. It's focused towards microfluidics in a lot of our work. We're separating chemicals and biological species. So we're doing chromatography, separating chemicals. We have a chemical mixture or a biological mixture, and then we're having a solvent pull the different ingredients of the chemicals and the biological species separate from each other. And we're developing structures by 3D printing, by laser texturing, and by developing microfluidic chips, moving from the expensive couple of 100,000 euro system down to a relatively quick, rapid, lower cost, but highly selective systems. This is a chromatogram, 5 different food ingredients separated. Another chromatogram, 5 different alkyl benzene from chemical production separated. And we can control all of the different variables, temperature, flow rate, for separation of these. Why are we doing this? The area for chemical and biological separation is worth tens of billions of euros per year. So it's quite a large market. If we can do this more cheaply, more selectively, at a faster rate, lower cost, it can have a big impact in industry and in terms of health of people as well. If you can detect a pathogen such as dengue fever, cervical cancer, other types of cancer in the blood, for example, if you can do that more rapidly, you have a better chance of successful treatment for the condition as well. So sepsis would be another example there, bacterial infections as well. I'm going to flick on from that. This is a list of some of the areas. We're looking at detection of herbicides, nitrates, and phosphates in water, DNA, particularly for dengue fever. We're looking at DNA detection at the moment. So you may be familiar with the Western blot, where you separate the different chemicals, the different species out at different points. You can functionalize the surface so that different elements will be separated to different points on the plate. And this is what we're doing here. Organic dyes, albumins, proteins, different protein separations, food ingredients. Cafestol and K-wall are 2 food ingredients that we're separating at the moment. These are shown just recently within the last 5 years to have an increase in bad cholesterol, and they're ingredients in coffee. So if you drink too much coffee, these ingredients are in there, and they're potentially increasing your bad cholesterol. They're in the oil in the coffee, so they get trapped in the paper. If you do paper filtering, it actually takes them out better than other methods of coffee manufacture. But there's a problem in detection of these elements from the matrix of the cafe. So we're looking at developing the microfluidic devices to do that. So effectively we're going from that 100 or 200,000 euro system up in the top left down to a thin film additively manufactured, rapidly prototyped textured surface of thin film, or a microfluidic chip where we add some tag in, we mix it in, and then we look at it in terms of fluorescence, photo absorption, or conductometric sensing. So these are some other examples. I'll flick through different modules. We can manufacture these as Lego brick modules. So once one gets used up, as it may happen in a chromatographic column, we can just swap that out for another chromatographic column. Looking at the DNA separation, photometric detection, different mixing channels, different Lego brick setups. Just to give you an idea of where this technology is at the moment, we can print the threads directly to go to above 100 bar pressure. Directly from these 3D printers, we can print transparent microfluidic devices and screw connections where we can just straight away work. There's no finishing machine required on these. Straight away there will be threaded connections getting pressure tightness up to and above 100 bars. These are DNA amplification modules with temperature control, heat exchanger control to control the temperature through lamp and PCR cycling to amplify the DNA species for detection. So in terms of the polymers, we have quite a large data bank of information right now, looking at the solvent compatibility, biocompatibility, transparency, the swelling effect of the different polymers from the different 3D printers, the dimensional accuracy, the surface energy controlled via laser texturing, so the wettability of the surfaces. We have a large database of information on the different polymers that are available for the 3D printers, so we can select a polymer that's appropriate for a specific chemical or a specific solvent in terms of the separation. Sometimes you just get the material safety data sheets. You don't always get the full ingredients of what's in these polymers that come commercially with the 3D printers. So we look at it in a bit more detail with AT or FTI ore to know exactly what's in there. So that's important for us because we need to know the functionality of the surface. Will it be able to absorb a specific chemical species that we're trying to detect and separate? So we can functionalize nanoparticles down into these Lego brick chromatographic columns and use them as SPE, solid phase extraction medium, so that we can pre-concentrate rather than looking at something that we may or not work. We can actually produce these quite cheaply and test them and see if they work before going to a full integrated system. Current projects we have are additive manufacturing and laser processing and fabrication of chromatographic systems. We're developing in dyes, additively manufactured dyes for some company where we are embossing dyes. We need to check the wear rate, the compressive strength, the durability of these materials for application in this particular project. So these are additively manufactured. We're basically proving principle of the process and the material for that particular project. Some other projects that we're working on currently are listed there as well. So just to say on the additively manufactured, there's a lot of scope in additive manufacturing for phase control. So you're melting and solidifying very quickly the different metal powder particles. So if you look at a conventional bulk metal solidification, whether it's a forging or whether it's a casting, you can only get to certain phases. However, if you can melt and solidify very quickly, as you do within the sector laser melting process, you can get new phases that you could never get through the bulk of the material. And one added nicety in that is that you can actually add in very small percentages of nano-reinforcement, silicon carbide, tungsten carbide, graphene, reduced graphene oxide. And we've done this recently. We just published a paper last month in Materials and Design where we've reinforced with 1%, 2% of graphene and reduced graphene oxide. And it's shown in this work that we've increased the hardness of the material by 40%. So compaction of the powders and sintering of the powders, yeah, we can do that. That's all pretty easy stuff. The hard part of this work is actually getting the nano-reinforcement to be uniform throughout the mixture of metal micron-sized particles, and that's where the research is ongoing going forward. These are some of the current projects. These are some of the current Horizon 2020 projects that we are applying under. Just to mention that this is our normal job. We're not a commercial entity. We do research for companies to develop products and processes for companies. So we would apply for innovation vouchers, feasibilities, commercializations, innovation partnerships through Enterprise Ireland. We would apply for industry fellowships where one of our staff members can go into the company to develop a project in the company, or somebody from the company can come into us and work with us to develop a specific product or process for the company as well. We work with center applications, proof of concept commercialization applications, partnerships where the cost modeling can be more flexible. And we also have a number of European mechanisms which we can apply directly with the company. We were lucky enough to get one H2020 award just on Monday this week, so that's a big success because they don't come through too often. But that's maybe interesting for some people here because it actually is to help Irish SMEs work with European SMEs, and the Irish SME can pull down €50,000 to develop something that's of interest for your company. There's some requirements on that. One is that it has to be with another European country, and the second is it has to be either in the space of biomedical, aerospace, ICT, agri-food, and within one of those discipline areas. So there's an opportunity there for the next 3 years to put down 50,000 per year for a project that's interesting for your company to develop a new product or process. And that's what we do, and there's lots of funding mechanisms for it, so we're there to help you prepare, get the funding, and do the innovation that you want to do. So thanks for listening, guys.
Thanks, Dermot. If I understand correctly, you're running a stable of off-the-shelf machines, essentially from the Optive family and the Fortis family, but you're running non-standard materials through them. Would that be correct to say?
Yeah. For the more expensive commercial machines, we tend not to change the materials because we invalidate the warranty. So for the next one, for example, we're not going to change the materials. But the lower cost ones, we will take the materials out, put in our own materials, and develop new materials that can be used for additive manufacturing. Yeah.
Okay. And then, do you need to modify the machines? Are they modded in some way, or will they just run that material?
So we do have cases where the pumps clog up and need to be replaced, or where the lines clog up and need to be replaced. But yeah, we're a research lab, so that's what we do. Yeah.
Thanks a million. Any questions from the floor for Dermot? No? Okay. Then I'm the last speaker. Thanks very much, Dermot.